If you live in a city, you drive by them every day. But you never have time to peek through the security fence. There's got to be 1,000 people working on them. How else could they go up so fast? How do they make all those parts fit? Who's responsible for what? If you always wanted to know what it feels like to straddle an I-beam hundreds of feet off the ground, or to run that massive tower crane, here's your chance to find out. Because we're going to construct a giant of a building from the ground up. We'll see the step-by-step process. Investigate the rich history of technological innovation that got us from there to here. Because every big building today owes a debt of gratitude to the groundbreaking structures of the past. And here, in the heart of Los Angeles, we'll meet the people who build one.
Tower crane operator, project architect, pipe fitting, bolt-up foreman.
For these hard-hat warriors, it's time for their close-up.
It's very dangerous. Very dangerous. Dangerous enough, you make a mistake, you could die.
As the building's going up, there's bound to be some trouble.
Let me spell it out to you. Grab number 1 right here, put number 2 right here, so I can get 1 and 2 in order here.
And here we go.
Despite the road bumps, Bobby, the man-lift operator, is on hand to lift their spirits.
This is a man-lift operator's life. You're always getting loaded and you're always having your ups and downs.
From the iconic Art Deco towers of the 1920s and early 30s to the shimmering monoliths of today, skyscrapers represent more than a collection of concrete, steel, and glass.
The skyscraper defines our cities. The skyscraper is a symbol of power, ingenuity, innovation, and will. A skyscraper is like a test bed. It's a place where we work out new technologies, new ideas, new construction methods as we try and build ever taller and faster and cheaper.
And the structure we're building is no exception. In May of 2002, the Clark Construction Group, the builder and general contractor, broke ground on a $174 million project in downtown Los Angeles. The task? Build a 750,000 square foot office building for the California Department of Transportation, or Caltrans. The building will take up an entire city block. And although it'll rise a relatively modest 13 stories above ground, with 4 stories of parking below the plaza level, constructing it will present the same architectural, structural, and mechanical challenges as larger buildings. Clark Construction has 27 months to complete our office building. Every big building starts with a developer or owner, someone who puts up the money.
The building is competent.
Typically, the owner selects an architect, someone to design the building. Sometimes this is done through a design competition, where rivals submit renderings and models of proposed designs in the hope of capturing a contract.
We have the address, the huge 100 here, but this will all be...
In the fall of 2001, Tom Main and his design team from Morphosis Architects are in the midst of a heated competition for the Caltrans project.
You put a huge amount of energy, and I'm talking about kind of emotional energy, not just intellectual and creative energy, but you get really involved in it personally. When you're done, you can't even conceive not winning.
For any competition, the developer gives rival architects a set of parameters called a program. It might include the amount of space desired, the intended usage for that space, and the budget. It's the architect's job to take these abstract concepts and numbers and fashion them into a workable building. Designers use every tool in their box.
The image is always the architect that is drafting for it, which is kind of an old image. It's all computer now. In the computer, we can do a model and rotate the model around, see it from any angle that you want to see it from, render it or shade it,
so that you can see kind of the surfaces more like you would see a traditional model.
And it doesn't have to stay in the computer. This machine can take this and that and turn it into this. It's called a 3D printer, and it works similar to your inkjet at home. A model starts out as a heap of plaster powder, which the printer spreads into a thin layer. The print head runs back and forth across the powder, spraying glue instead of ink. It's creating a cross-section. When it's through with one layer, the printer drops the base a fraction of an inch, spreads another bed of powder, and sprays more glue.
Eventually you end up with a kind of cylinder of plaster that you can vacuum out the excess, and you're left in the end with a three-dimensional model that you can discuss with the team.
The 3D printer quickly renders concepts, but they're just to stimulate debate. For the actual competition, designers will spend hundreds of hours making detailed models with paper, plastic, and glue. Others on the team will work on the guts of the building. If they win the competition, Morphosis will eventually lay out every detail, every column, every window in the form of extremely detailed drawings or construction documents. The set of documents can be 300 to 400 pages, and they're constantly changing.
Designing is not just making one decision after the other, it is making a whole bunch of decisions together, and they all have to work together.
Architects don't work in a self-indulgent creative vacuum. They're governed by planning codes, structural engineering limitations, the needs of the client.
You can either have moving exhibits, but you're going to have a very large archive of these fine art photographs.
And, to the frustration of many architects, the budget.
On the shoot, even if it has nothing to do with mechanical, just so you know.
The architect also consults a series of additional specialists, like the structural engineer, who designs the support framework of the building, and the mechanical engineer, who figures out how to air condition the building.
Architecture, like watching a child growing. A parent can want them to go this way, and maybe a little bit this way, and maybe they go that way, and finally they're just their own person.
On November 12, 2001, Morphosis gets word from Caltrans that it has won the competition.
I think it's going to be pretty interesting.
Now, like any other high-rise designer, Morphosis architects have to produce the mountain of construction documents that a builder can turn into a structure.
Ready? Let's go.
It all starts with digging a massive hole and shooting some concrete. Yep, it's gonna get messy. Before the Caltrans building or any large building can go up, it's got to go down. More than a cliche, creating a solid foundation is essential.
This building will be supported on spread footings. Spread footings are basically a rectangular or square concrete block, in this case about 18 feet by 18 feet by 4 foot deep, that support the structural steel columns.
The Caltrans steel superstructure will weigh 13,000 tons. But fortunately, rock near the surface can carry the load. When a site has mud, soft soil, or weak rock, a builder might have to drive piles, pounding long pieces of concrete or steel down to bedrock. Piles won't be necessary for the Caltrans building. But before concrete pouring for the footings can begin, builders have to dig the hole. It's the pit on top of which the building will sit. To get the digging done, the excavation subcontractor uses specialized tools. Giant excavators, bulldozers, semis, a paleontologist. Paleontologist?
I'm a field paleontologist, and it's my duty to find fossils and recover them and bring them back to a museum.
It's a requirement in most states that a specialist like Conrad be on hand during excavation, in case artifacts are inadvertently uncovered. Here, a backhoe becomes a time machine.
Some of the interesting fossils that we have found have been great white teeth. This is a fossil great white shark. It's approximately 3 million years old.
But a big find is often the last thing a construction company wants when they're fighting a deadline. One of the biggest construction-related finds happened in 1991 during excavation for a new federal building in Lower Manhattan. Builders uncovered hundreds of burials from an African cemetery, halting construction for several months while archaeologists excavated the remains.
It's essentially like a big treasure hunt. That's what keeps the drive and the interest going. You know, you're going to find that one awesome site that's going to make you famous.
Even at the excavation stage, this project takes an enormous amount of planning and coordination. That's where the general contractor comes in. On this project, that's Clark Construction.
It's miscellaneous items. No personal vehicles on site. Everybody can tell the site's pretty congested and we don't want to. Clark's job is to coordinate the subcontractors, to schedule the work, and to make sure it meshes as smoothly as possible.
There are more than 55 subcontractors who will actually do the construction. The general contractor oversees this organized chaos.
This represents the true schedule for the project. There are over 5,000 activities. Each of these events has to happen in a particular order within the context of the construction of the job.
I don't know why this can't be done. Is there any reason this can't be done? Absolutely not. Can you kick them any and get them done? How you doing there, Sparky? Pretty good. Good. And that ladder say that you can't go on the last 2 steps? Almost every ladder I've ever seen, you're close to a shaft. I'd hate to see you go down.
The general contractor is like a big traffic cop. And sometimes one of the subs needs some direction.
2 weeks ago, they said there's no problem. Well, if there's no freaking problem, why isn't this done?
The general contractor always has a lot at stake. He's promised the owner his company can construct a building by a certain date and for a certain amount of money. In this case, $174 million. The first scheduled move-in date is August 12, 2004, only 18 months away.
There's nothing supported.
Adding to the pressure, Clark Construction faces penalties of $25,000 for every day past their promised completion date.
Most large construction projects do have penalties involved with them. Obviously, a building needs to be rented or leased or used, and the user needs to know when he's coming in, and it costs money to rent a building someplace else, so this building has to be done on time. We will be on schedule no matter what it takes. We will make it happen.
After the excavation company has removed 200,000 cubic yards of dirt, the concrete subcontractor comes in next. This project will take 36,000 cubic yards of concrete for the foundation and floors.
There's a few different ways to place concrete. One is you tailgate it out of the back of the truck. Another way is you pump it into a form or into place with a concrete pump. And then there's what is called shotcrete pump, which is this application here. Shotcrete is where it's actually blown onto the wall with high air pressure. It's a lot faster to install it.
Modern construction couldn't do without the magic concoction of sand, aggregate, water, and cement. Although cement mortar dates back to at least the Romans, modern concrete construction wasn't possible before the invention of Portland cement in 1824 by Joseph Aspdin of England. He burned and ground together a mixture of limestone and clay, creating modern hydraulic cement. It hardens with water and gets stronger with time. By 1900, engineers were using concrete to construct bridges, streets, and buildings. To make concrete stronger, builders started embedding steel reinforcing bar, or rebar, into the concrete. Concrete performs well under compression, but not as well under tension. Steel, on the other hand, performs much better under tension.
So the two together, the concrete and the reinforcing steel, will then resist both compression loads and tension loads.
Builders use reinforced concrete in foundations, walls, floors, and sometimes structural columns. These guys make it look easy, but concrete can be exceptionally tricky once in a while.
Concrete is like a woman. You have to be patient with it. It sets up at its own pace, and it's not very agreeable at times.
After the foundation work, it's time to bring in the real men of steel. The High Wire Act is about to begin. What can you do with 13,000 tons of steel? Well, you could produce 17,000 SUV bodies, or 280 million soup cans, or our downtown LA behemoth. Now that the foundation's set, it's time to erect the skeleton. Large buildings are supported internally by a steel or reinforced concrete framework. And the first steel to go into a building is always a big event. There's a charge in the air as spectators watch the tower crane swing the first steel column into position.
Hey, their hole isn't big enough over here. Their concrete hole isn't big enough.
Oops.
Right one. 3014. Come down a little, Dino, and see if we can get it wedge in there.
This is the very first column, and you've got a problem. When you start a job off and have a problem right at the beginning, you wonder what the rest of the building's going to be like.
The template used during concrete pouring was smaller than the actual column. Nothing a jackhammer can't fix. And in a few minutes, the first column drops into place. One down, 7,125 pieces to go. Fortunately, there's just a few holes needing enlargement. In no time, steel's a-flying.
Well, we basically have four separate gangs. The first one we have is the raising gang, and they're responsible for erecting all the structural steel. Then we have the bolt-up gang, which is responsible for bolting it all. Then the plumb-up gang comes by, and they're the ones that plumb it. And we have the welding gang, which, after all the bolting's done, they go ahead and weld it.
By most accounts, the two connectors, who are part of the raising gang, have the most difficult and dangerous job on the site.
The connectors are the ones responsible for joining all of the steel together. Every stick of iron that you see here is put up by two individuals and a crane.
The piece comes in, we're supposed to put two bolts in on each end, one's supposed to be wrench tight, and then they come afterwards and put all the bolts in. Our job is just to get the iron up as fast as we can.
You don't get to make a lot of mistakes in that part of it. So, you know, these guys they're always on the edge all day long.
You just don't look down. You just do your job and you go home safe. Go home to your family.
For more than a century, it's guys like these who've risked life and limb to build metal monuments across the country.
The ironworkers' trade really begins with the construction of bridges. Bridges are the structures which are most technologically challenging in the late 19th century.
The profession attracted independent spirits, daring types, who either conquered their fears or weren't born with any. But one group of people seemed almost predisposed for the high wire work. The Mohawks.
Mohawks started building bridges in Upper New York State and Canada in the 1860s and 70s. They were really good at it, and the jobs were very good.
Originally hired as day laborers, the Mohawks and other Native American groups quickly earned a reputation as exceptional iron workers. It
became apparent to all concerned that these Indians were very odd and that they did not have any fear of heights. If not watched, they would climb up into the spans and walk around up there as cool and collected as the toughest of our riveters.
When engineers redirected the technology of steel bridge construction vertically into skyscraper building, many Native American ironworkers continued in the trade, helping to erect iconic skyscrapers like the Empire State Building and the World Trade Center.
Mohawk steelworkers still work on buildings today, and they're in at least their fourth generation. And this is true of other steelworkers too. The jobs get passed down from generation to generation.
But some of the legends about gravity-defying Native Americans and the high steel might have become bigger than the buildings they helped erect.
I think that there's a myth that suggests that all of the skyscrapers' frames were constructed by Mohawk Indians. It's true that some ironworkers are Native Americans. It's also true that some ironworkers are Irish Americans or Italian Americans. Ironworkers are very diverse, just as America is a very diverse place.
And they played an important role in building skyscrapers and bridges in the city, but they were probably no more than 10% of the workforce at any one time.
But 10% of the workforce is worthy of Mohawk bragging rights, considering they're less than a fraction of 1% of the combined U.S. and Canadian populations. On the high steel, it doesn't matter what the iron worker's ethnicity. What counts most is teamwork and good communication.
You gotta have a partner, and you gotta be able to work together, because if he does something dumb, it's gonna get both of you hurt or one of you hurt. So you gotta be right on the same page the whole time and know what each other's doing. I work with him great. We get along perfect, me and my partner.
Working in a high-risk situation, a raising gang has to develop a strong sense of trust. It's this sense of camaraderie that holds this building together. That and about 89,000 bolts.
Usually got a couple guys stuffing bolts behind the raising gang, and another two guys tying up the bolts behind the plumb-up gang.
Before the mid-1950s, builders used rivets to hold connections together. A riveting gang consisted of a heater who made the rivets red hot. With tongs, the heater tossed each rivet to the catcher, who used a tin can to make the grab. The catcher struck the rivet against a beam to shake off the glowing flakes and rammed it into the hole. The bucker-up held one end, while the gunman pounded the rivet with a pneumatic hammer. While an experienced riveting gang could drive 500 rivets a day, in the mid-1950s, builders started using bolts, which were just as strong as rivets, but faster to install. They also required fewer laborers. Iron workers on this job bolt and weld the joints to create a rigid skeleton. And it was the invention of the internal steel skeleton like this that sent skyscrapers soaring more than 150 years ago. Before the 1840s, the weight of the floors in most multi-story buildings was supported by the exterior load-bearing walls. But engineers were restricted on how high they could build because the walls at the base had to be very thick to support a tall structure. In 1848, James Bogardus introduced a way of supporting a building not by its exterior walls, but from within.
So instead of having a masonry pier in the middle of your building, you'd have a cast iron column. Instead of having a masonry exterior wall, you'd build a cast iron wall.
In the late 1800s, engineers started using steel, which was stronger than cast or wrought iron. This new cage or skeletal construction offered many benefits. The load of the building was distributed equally over the internal frame, instead of entirely by the exterior walls. This allowed for taller structures with larger windows, thinner walls, and therefore more rental space. Then all the pieces were in place for the birth of a uniquely American style of architecture.
The first building to employ steel cage construction was the home insurance building in Chicago, designed by engineer-architect William LeBaron Jenney.
Built in 1885, many scholars consider the home insurance building to be the world's first skyscraper. Although Jenney's building was only 10 stories tall, it had all the essential ingredients. It had a fireproof metal frame. It also had elevators, which were essential to the development of tall buildings. With the key elements in place, the skyscraper was set to take off. Fueled by an economic explosion and inflated egos, the world would soon see how high buildings could climb. The Caltrans building is also starting to climb. The iron workers are making fine progress. Then, 3 months into steel erection, one event rocks the job site, underscoring the hazards of the profession.
A very unfortunate accident where a young steelworker fell and was killed, and it's really upsetting to me and the staff and to the other people who worked on the project that a young man had a very tragic accident and lost his life.
Despite all the safety mechanisms being in place, such as safety cables and nets around large openings, Michael Jesus Del Rico fell 4 floors to his death. He leaves behind 2 daughters.
We're going to go ahead and get started with safety as usual. Zach's going to be working with Corey on safety.
Even in the era of OSHA regulations and safety inspectors, construction has the highest number of fatalities of any industry classification, accounting for around 20% of total work-related deaths. Sadly, this monument has also now become a memorial. It's 6 o'clock in the morning when Rick Fuller climbs the 289 steps to his office in the sky. Rick operates a giant tower crane, the biggest tool on the job, and one of the most important.
There's lots of people on the ground under us. We're pretty much responsible for looking out for anybody that's under the load and keeping the load from hitting anything while it's in the air.
Rick controls the crane with 2 joysticks. The lifting is done with an electric motor, which spools the 1-inch steel cable in or out like a fishing reel.
Well, the crane operator, he's got to trust us, and we got to trust him, because he messes up, we're dead pretty much, or someone's going to get hurt.
From where I'm sitting, people look like ants on the ground.
Luckily, he's getting some help from the phone man down below.
Hi, I'm choker.
Hey, you got to go to air in a little bit.
Down, boom out, sink hole.
The crane doesn't operate in high winds. Still, it bends and flexes, even with normal loads. It can move as much as 1 foot side to side. A little disconcerting when you're 300 feet in the air.
Yeah, you try not to think about it. It's all these gray hairs. I wasn't gray before this job started.
Rick's job is to put together the internal steel skeleton designed by the structural engineer.
The building is the top of it.
While the architect gets most of the glory, it's the structural engineer whose behind-the-scenes work ensures a building can stand up, won't blow over in a typhoon, or fall down during an earthquake.
The forces that act on a building, of course, is the vertical load, which is from the load of the building, as well as the occupants in the building and the contents of the building. We call those gravity loads because they're acting downward vertically. Then we have the horizontal loads, which can be either wind loads or earthquake loads. The bigger the surface area of the building, the more wind load that building is going to be taking.
If a building is too flexible, wind can cause large swaying motions. If a building is also light, the swaying can be relatively fast. The combination can make occupants seasick. Buildings with larger members, more rigid connections, or more braces are stiffer and don't sway as much. Also, buildings that are heavier sway more slowly, creating an easier ride for occupants.
Stiff sounds great if you're worried about wind and tenant comfort in windy conditions. Stiff is not such a good thing when you're dealing with earthquake. In earthquake, when the ground moves, the building is left behind, and then it catches up. The stiffer the building is, the more force it attracts.
The structural engineer must therefore choose the best framing style for the building's specific location. There are a few telltale signs the Caltrans building is going up in the heart of earthquake country. Designers actually engineer structural weak points, called dog bones.
Now those notches are there so that the engineer knows where the beam will buckle in an earthquake. So with the dog bone in there, the columns should not be damaged. So the building will be able to stand safely after an earthquake. But the beams may be damaged and may have to be repaired. But again, the building will be safe, for the occupants to exit.
Beyond the seismic features, the framing of the Caltrans building is essentially the same as the first steel cage buildings.
The Empire State Building was the high point, metaphorically and physically, of this kind of construction.
Built in 1931 and the tallest skyscraper in the world until 1972, the Empire State Building was also a very heavy building. Iron workers erected 60,000 tons of structural steel. The limestone and granite cladding also added weight. The combination of weight and rigid connections made the building very stable, even in high winds. But in many ways, the iconic skyscraper signaled the end of an era. The high-rises built after World War II came to embrace the international style, which celebrated the austere beauty of metal and glass. Construction materials, including steel, became lighter and stronger. But structures built with lighter materials risked becoming too light and flexible. To stiffen structures, engineers started adding diagonal bracing around the internal vertical cores of buildings.
If you were to take some popsicle sticks and just glue them together, if you put a lot of glue on those joints, obviously it's more rigid. And if you've then added some diagonal members to it, you can almost see the picture that it's even more rigid. So that's the way to resist the horizontal loads.
A more radical approach introduced in the late 1960s was to move the bracing to the exterior of the building.
The perimeter brace tube system most famously was used on the John Hancock Center in Chicago, Illinois. Everyone in Chicago can see these giant X's marching up the side of the building.
Designed by the innovative engineer Fosler Kahn of Skidmore, Owings & Merrill, the John Hancock Center is a departure of sorts from traditional skyscrapers. Called tube construction, this design uses exterior diagonal braces connected to columns to resist some of the gravity load and absorb all of the wind load. Completed in 1969, the revolutionary design opened up valuable workspace because it required fewer support columns. The most famous tube design buildings were the Twin Towers of the World Trade Center. Closely spaced columns created an exoskeleton. Another building that uses the tube design is the Sears Tower in Chicago, which works like 9 tubes bundled together.
Engineers working with architects are always balancing how tall, how wide, how many columns, how big a window, how fat a column, how deep a beam. It all has to be balanced. There's no one magic answer.
But what if Mother Nature throws you a bunch of curveballs? How would you construct the world's tallest building in both a seismic region and one regularly hit by typhoons? Builders of the new Taipei 101 face such challenges. It's been 5 months since the beginning of steel erection on the Caltrans building. Because Los Angeles is in an active seismic zone, the steel members are more beefy than those used in similar-sized buildings in most cities. However, some regions of the world have even more of nature's fury to contend with. In 1999, construction began on Taipei 101 in Taiwan. It would become the world's tallest building. But their structural engineers faced huge obstacles.
Extreme earthquake happens about every 50 years in Taipei and in Taiwan area. So the earthquake design is the most important part of all the structures in Taiwan.
Taipei is also regularly pounded by very strong typhoon winds. A structural engineer would like to handle these two forces in different ways. A light and flexible building is better at withstanding earthquakes, while a heavy and rigid structure resists excessive wind loads better.
In Taipei, you have the situation, what do I do? Seismic had to be addressed first. So they went with a building construction system that is light. They use a steel frame system. Then they had to make it stiffer so that it didn't sway so much. They did that by having a braced core, but the building is so tall, the core alone is not enough stiffness. So they have outriggers. They have horizontal trusses that reach out every 8 floors and grab outside columns.
These 8 super columns are large hollow steel boxes.
The biggest size is 8 feet by 10 feet. And then we fill in the column with very high strength concrete. And inside the concrete, we also provided a lot of large size rebars. The steel is good for tension, but the concrete is very good to provide the compressive strength.
In 2003, the Taipei 101 tower captured the title of world's tallest building and a great deal of media attention. At about the same time, the Caltrans building was in the spotlight as well, but for very different reasons.
Our tower crane was essentially hijacked, which made several national news venues. There was a distraught gentleman. He was a former crane operator, and evidently he had been drinking. He hopped over our construction fence, climbed up 220 feet of ladder, and began to wildly operate the crane.
I turned on the news at 10 o'clock, showed the guy actually walking out on the jib with a bottle of something in his hand, waving at people and drinking.
Police feared the man might jump or have a weapon. The SWAT team was called in. After 7 hours of negotiations, the man came down and was arrested.
I'll shove it up.
Fortunately, no one was hurt. And despite the interruption, steel erection continued right on schedule. The internal skeleton neared completion. When the last stick of iron goes into a building, whether it's the Empire State Building, the Pan Am Building, or our Caltrans building, it's always a reason to party. On June 13, 2003, 10 months after excavation began, the Caltrans project celebrates the topping out ceremony.
We're so overwhelmed that we can't even express how important is this, but that is a big day for any construction site. This is why we usually have these parties.
It's a big party with a barbecue and a much-deserved day off. The main event is the ceremonial hoisting of the final beam into position. Before it goes up, everyone signs the top-out beam. Historically, some sites have placed a tree on the top-out beam, a custom dating back to at least 700 AD. No tree here, but plenty of Sharpies. The beam sports hundreds of John Hancocks, representing the diversity of the people needed to get a building of this size off the ground. Politicians to pipe fitters, figureheads to foremen, and everyone in between.
Now the real work has started.
Today is really District Director for District 7. Thank you, Doug.
Gotta get this hooked up, because right after this speech, they want this to go.
Thank you so much.
And with that, the tower crane hoists the final beam into place. It's been a big project.
This is one job I'll look back on for the rest of my life and be proud that I was a part of it.
Coming back a year down the road or 2 years down the road and looking at something that you had, had a hand in, in building, there's a great sense of accomplishment there.
Although there's plenty more to do before this building is ready for elevators, air conditioning, and plumbing, we've gotten the skeleton up. The iron workers can leave knowing they've done a great job.
I love my job. I wouldn't want to do anything else. Unless it didn't have to work for no money. I'm proud to be an iron worker.
Brandon and Aaron have built a dozen buildings, but this will be the last one they do together as partners.
We worked together for how long? 2.5 years? 2.5 years together. Every day. Like a married couple. I see him more than my wife.
Now they're going to separate jobs. But how are these two friends who've trusted their lives to one another going to handle the split? Will there be a sentimental goodbye?
Thank God we're done.
Guess not.